This is a revision session for paper 1, assessment window 2. So on the screen, you should have the revision list that you all have had already with the different topics that we're going to be assessing on paper 1 on them for the higher paper. So I'm just going to go through these in order of grade. So starting with the blue topics, then the green, and then the orange. Okay, so question 1, express 120 as the product of powers of its prime factors. So we might also know this as prime factorization. So to do this, I'm going to start with 120 at the top and think of two numbers that multiply together to make 120. So I'm going to go for 60 and 2. You can use any numbers that you like, and we should get the same answer no matter what. If it's a prime number, we circle it. So remembering your prime numbers are 2, 3, 5, 7, not 9, because that's in the 3 times table, 11, 13, and so on. So they're numbers that can only be divided by 1 in themselves. So 60, we could say that's 30 times 2. And 30, we could say that's 10 times 3. And 10, we could say that's 2 times 5. Now, no matter what method you choose, you should always end up with the same numbers circled. So if I'd started at the top by doing 12 times 10, I still would end up with the same answers. Now, the most common mistake I see here is people writing them with commas. You must write them as the product, so that's the multiplication of those numbers. So 2 times 2 times 2 times 3 times 5, and you can also write that as 2 cubed times 3 times 5. Then it says find the lowest common multiple of 120 and 150. So we've just done the prime factorization for 120. If I do the prime factorization for 150 as well, and then we can do the Venn diagram, so that would be the best method for this one. So this is 3 times 50, circle the 3. 50 is 5 times 10, and 5 is prime, and 10 is 2 times 5. Now remember your timesing. A lot of people take 10 and they do 5 and 5. But remember, 5 times 5 is 25. So if you find it helpful, you can always put multiplications between each stage, and that will help you remember that you're trying to do a multiplication there. So my answer for 150 is 2 times 3 times 5 times 5. We can now do our Venn diagram. So we'll do a circle for 120 and a circle for 150. And we'll put our numbers in. So we can see that they both have 120 was 2 times 2 times 2 times 3 times 5. So we're comparing this with this. So we can see that we can put a 2 in the middle because they both have a 2. We can see that they both have a 3. So we put that in the middle. And we can see that they both have a 5. The 120 has got 2 more 2s, so they go out here. And the 150 has got another 5, so that goes out here. Now, if I wanted the highest common factor, I would just be multiplying the numbers in the middle together. So the highest common factor is 2 times 3 times 5, which is 30. But because I want the lowest common multiple, I want to take that answer, 30, and times it by what's left on the outside. So 30 times 2 times 2 times 5, which is going to be 120 times 5, which is 600. So that would be my answer. What we've essentially done there is found the first number that's in the 120 times table and the 150 times table, and that's 600. The lowest common multiple, because it's a multiple, it's going to be bigger. It's in both their times tables, bigger than both the numbers. Okay, next question. This is going to be Pythagoras. Yes, good. So we've got 2 sides and we want to know the third side. So I know that this side is 16 centimeters, this side is 8 centimeters, and we're being asked to find the length of QR, which is this side here. Now, because I'm being asked to find the shorter side, remember that opposite the right angle, that's the hypotenuse. So because I'm being asked to find the shorter side, we're going to do 16 squared, take away 8 squared. Okay. Let me just grab my calculator. 16 squared is 256. Take away 8 squared, which is 64. And then we're going to square root that answer. So that is 13.5. 8564, blah, 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 blah. So to two decimal places, we're going to say 13.86. Fab. Okay, next question. There's another right angle triangle, another Pythagoras question, but just to show you going the other way. So here we're going to do a squared plus b squared. Because we want the longest side, we want this side here, we're going to add. Before we wanted a shorter side, that's why we subtracted. Here we want a longer side, so we're going to add. So we're going to do 1.7 squared, add 3.2 squared. So 1.7 squared, 2.89. And 3.2 squared is 10.24. Add them together, and we get 13.13, but that doesn't mean that that's the length of our side. That's c squared, so we've got to square root that answer, and that gives us 3.6235, and we're giving our answer to three significant figures in this one. So 1, 2, 3, 3.62, because the next numbers are 3, so that wouldn't round it up, that would keep it the same. So that's Pythagoras. Square them and add them, or square them and take away, depending on whether you want the longest or the shortest side. Okay, the radius of the circle is 3.6 meters. Work out the area of the circle. So for the area of a circle, we need to remember the formula pi r squared, which is pi times the radius squared. So pi times radius times radius. So we're going to do pi times 3.6 times 3.6. Which is 40.715. And we're doing that to three significant figures. So 1, 2, 3. So it's going to be 40.7. Now in the revision list, it says to be able to work out the area of a quarter of a circle. So if I'd only asked you for the area of a quarter of this circle, if I just asked you for the area of this bit, for example, we would have done exactly the same thing. But at the end, we would either multiply our answer by a quarter, or very simply just divide by 4, half it and half it again. If we only want a quarter of the circle, we can just divide it by 4. Okay, Daniel bakes 420 cakes. He bakes only vanilla cakes, banana cakes, lemon cakes, and chocolate cakes. 2/7 of the cakes are vanilla. So we've got vanilla, banana, vanilla, banana, lemon, and chocolate. So 2/7 of the cakes are vanilla. So if we want 2/7 of 420, if we want a fraction of a number, remember we divide by the bottom and times by the top. So 420 divided by 7 is 60, and 60 times 2 is 120. So we have 120 vanilla cakes. 35% of the cakes are banana. So if we want 35% of 420, easiest way to do that, because we have a calculator, is to do 0.35 times 420. 0.35 being the decimal equivalent of 35%. So 0.35 times by 420, which is 147. And that's the number of banana cakes. The ratio of lemon to chocolate is 4:5. Now that's only looking at lemon and chocolate. So we don't want to use 420 for this, because the 420 would involve the vanilla and the banana. What we want to do is add those together to get 267. We add these, 120, add 147 is 267. And we want to take that away from 420 just to find out how many we're working with for lemon and chocolate. So 420 minus 267. Then again, you've got a calculator, so you can use your calculator for this, or you can just do it like this, 153. So we've then got to split 153 in the ratio 4:5. Now I find with ratio, it's really nice and easy if you draw your little lines. So 4:5. Okay, forgive me, I'm gonna have to pick up where we left off. So we had 153 in the ratio 4:5. So we need to divide that into 9 equal piles. That's the total for all of this. So 153 divided by 9. Again, I'm just going to use my calculator because we can. It's a calculator paper. So 153 divided by 9 is 17. So that means every line's got 17 on it. And so if we want to know the number of lemon cakes, that's going to be this size because it says the ratio of lemon to chocolate is 4:5. So lemon on this side, chocolate on this side. Lemon cakes, therefore, is 17 times by 4, which is 68. So just make sure that for that topic, you're really confident with how we work out, how we calculate ratios, how we calculate fractions and percentages and so forth. Okay. Let's hope it doesn't crash again. Okay, ABC is a right angled triangle. And we've got to work out the length of BC. So BC is this side over here. So I'm just going to put an X there so I know that that's what I'm going to work out. Now this again is a right angled triangle, which makes me think it's either going to be Pythagoras or SOHCAHTOA. But because we've only got one side and we want to know another side, I can't use Pythagoras. And there's an angle involved, which makes me think it's going to be SOHCAHTOA. First thing we do is label our side. Now, over from the right angle, that's your hypotenuse. Between the two angles, that's your adjacent. And over from the interesting angle, that's going to be your opposite. Now we want to think, what do we know? What do we want to know? And what do we not care about? So in this example, I know the adjacent, that's helpful information. I want to know the opposite. I don't know the hypotenuse and I don't want to know the hypotenuse. That's not what we're trying to work out here. So A and O tells me that this is going to be, if you think about your triangles, sorry, I could draw these better, couldn't I? Or TOA. Now, of those three triangles, the one that has the O and the A involved is going to be TOA. So that's the one we're going to use. So think about your TOA triangle, cover up the thing you want to know, and do the sum that's left behind. So in this case, we want to know the opposite. If I cover up the opposite, I'm going to be doing T times A. Now think about what that means. T is tan 36. Times by the adjacent, which is 8.7. I'm going to type that on my calculator. So tan 36, not forgetting to shut the bracket after the angle, times by 8.7, which is 6.32. Okay, now if I'd been using SO, then I'd say it's sine 36 for S. If I'd been using CA, I'd say it's cos 36 for C. Cover up the thing you want to know and do the sum that's left behind. If I'd wanted to know the adjacent and covered that up, I'd have been doing the opposite, divided by tan 36. So just covering up the thing you want to know and do the sum that's left behind. Okay, next question. Describe fully the single transformation which takes shape A onto shape B. Now, when you're asked for a single transformation, you've got a choice. You've got translation, rotation, reflection, or enlargement. And because they're saying describe fully the single transformation, you are only allowed to write one of those words. And as soon as you write more than one, the examiner thinks that you're hedging your bets or trying to give more than one answer. So if it says the single transformation, make sure you're only picking one of those words. It is going to only be one of those, not it's been rotated and then moved, or it's been enlarged and then translated. Nothing like that, okay? It's only going to be one of them. And hopefully we can see that in this case, it's been enlarged. So for the first mark, we're going to say shape A has been enlarged. Now that would get me 1 mark because I've picked the transformation. Scale factor, now that's important. That's going to be our 2nd mark. We can see here that it's 1 and here that it's 3. So it's 3 times bigger. The other thing you can do is big divided by small. So if we pick another corresponding side, let's say we pick this side and this side, that's 6 divided by 2. And we can again see that it's 3 times bigger. Okay, so 3 times bigger, so scale factor 3. That's going to get me my 2nd mark. 3rd mark is from the point. And we need to give the center of enlargement. Now, to get that center of enlargement, we're going to connect the corresponding points. So this point is the same as this point here, and we just keep going back with it. This point corresponds to this point here, and we keep going back with it. This point corresponds to this point here, keep going back, and this point corresponds to this point, and keep going back. So you can see that all of those lines come together at the origin. So we would say that this shape has been enlarged from the point 0, 0, or you could write the origin for that question. Shape A has been enlarged, scale factor 3, from the point 0, 0. There we go. Describe fully a single transformation. So I just want to show you this one. This is a negative enlargement. So it's still an enlargement, still bigger. Describe fully the single transformation. So shape A has been enlarged. And that's still going to get us a mark. It's bigger. It's not been rotated as well. Now what's happened? Oh, how did I do that? Magic. We'll leave it as my handwriting, I think. Shape A has been enlarged. Scale factor. Now this is 1, 2, 3, 4. And this is 1, 2. So we've gone from 2 tall to 4 tall on that straight side, or you can look 2 across, 4 across. But because it's been inverted as well, this is going to be a negative enlargement. So this is actually scale factor -2. Now, the reason I know it's a negative scale factor is because it's gone through the center of enlargement and back out the other side. The reason I know that's happened is if I take the corresponding points now, so this point is this point. This point here is this point here. This point here is that point over there. This point here goes down to that corner, and this point here goes down to that corner. So it doesn't look very neat, but hopefully you can see that when we join all those points up, we get a center of enlargement that actually is between the two shapes. So here, this is our center of enlargement. And we need to write that as well for our third mark. Center of enlargement, or from the point you can write, 2, 2 in that case. So that only happens when it's a negative scale factor. Now, if it had been a positive scale factor 2, A would have carried on and got bigger, and the shape would have been like down here. It would have been bigger from the center of enlargement. The only way that you end up with that inversion is if it's a negative scale factor as well. So it goes through the center of enlargement and back out the other side. Next question, we have a box plot. So the table gives some information about the heights of 80 girls. The least height is 133. Now 133 is here, so I'm just going to do a line at 133. And the greatest height is 170, so I'm going to do a line there. The lower quartile, now that's 25% of the way through the data. That's 145, so 1, 2, 3, 4, 5. 157 is there for the upper quartile, and the median is 151. Okay, so those are all my key pieces of data, and we do lines, and we make the middle 3 into a box, the median, the upper quartile, and the lower quartile. And the size of that box is called the interquartile range. So this measurement here is the interquartile range, and that would be the top number here, take away the bottom number here. So the size of that box from 145 up to 157, so 12. So the interquartile range in this question is 12. And then we just need to do 2 lines going out to the edge. So this one here and this one here, and that takes us out to our smallest value and our biggest value. And if we were asked for the range, remember your range is your highest takeaway, your lowest. So the range would be from this value up here, 170, to 133. So the range in that case is going to be 37. And remember, they're both spreads of data. You've got 25% of the data here, 25% of the data here, 25% of the data here, and 25% of the data here. And we would want to label, I think in this question, there was a boys ones as well. So girls' heights. I just want to put that there. Fabulous. So that's that. That's the interquartile range, which is the upper quartile take away the lower quartile, and the range, which is the highest take away the lowest. We've got the smallest here, lower quartile, median, upper quartile, and the highest value. Okay, next question. There are 3 dials on a combination lock. Each dial can be set to one of 3 numbers, 1, 2, 3, 4, or 5. The 3-digit number 553 is one way that the dials can be set, as shown in the diagram. Work out the number of different 3-digit numbers that can be set for the combination lock. So to answer this question, we need to think about the number of different options for each position. So if I think I've got position 1, I've got position 2, and I've got position 3. So if we think of position 1 as this top wheel, how many different values can that take? Well, it can be a 1, a 2, a 3, a 4, or a 5. So we have 5 different options. Times by how many different options have we got for the second position? Well, that's also going to be 5 because we've got a 1, a 2, a 3, a 4, or a 5. And same for the third position. We've also got 5 different options for what that one can be. 5 times 5 times 5 is 125. So that would be my answer for that one. Quite nice and straightforward. We just have to multiply the options together. Slightly more difficult version. In a restaurant, there are 9 starters, 15 mains, and 8 desserts. Janet's going to choose one of the following combinations. So she might have a starter and a main. Now, if she does a starter and a main, that would be 9 times 15. So there are, how many different ways can she pick a starter and a main? Well, 9 times 15 is 135. So there's 135 different combinations of starter and main. Or she might just be fancying a main and a dessert. Now, if she wants a main and a dessert, it's going to be 15 times 8. 15 times 8, 120. Or she might be pushing the boat out and deciding that she's going to have a starter, a main, and a dessert, which would be 9 times 15 times 8. They're all the different things that she can pick, which is 1,080. So there's 1,080 different ways that she could have a 3-course meal. Show that there are 1,335 different ways to choose a meal. Well, if she goes for a starter and a main, that's 135 options. Add, she could go for the other way, that's 120 options, or she could go for a third way, which is 1,080. If we're adding all of that together, we get 1,335. So we've shown that that's how many different ways she can choose her meal. Okay, next question. This is going to be the sine rule. Now, the reason I know this is a sine rule is because I've got a non-right angled triangle. So we haven't got a right angle. It's not going to be SOHCAHTOA because we haven't got a right angle. And I've got a pair. Now, if it was going to be the cosine rule, you'd know maybe this side, and you'd know the angle in between, 35 degrees, let's say, and you'd be being asked for this one over here. So if you had 2 sides and the angle in between, and you wanted this one, that's going to be the cosine rule. But for the sine rule, we work in pairs. So we know that this 15 and 112, because they're opposite each other, they are a pair. Now, we would like to know the length of BC, which is this one over here. We put what we want on the top. So if you A over sine A equals B over sine B. So we're going to put the sides on the top because that's what we're looking for. Now, replacing that with the pairs, so x over sine 33 equals 15 over sine 112. So we're just putting what we want, we're putting the pairs together and putting what we want on the top. That makes it really easy to rearrange. So if I want to know what x is, I'm going to multiply both sides of my fraction by sine 33. So x equals 15 over sine 112 times by sine 33. Typing that in my calculator, 15 over sine 112 times sine 33. And that gives me 8.811. And that'd be centimeters, whatever. It would tell you what to round it to. No. Okay, transformations of functions. So the graph of y equals f of x is shown on the grid. Now, f of x is just a function of x. So they've drawn something on the graph. They're calling it a function, and we're going to do something to it. Now, if you're given y equals f of x add 2, what's really important to remember with transformations of functions is that anything inside the bracket is affecting the input. And so any change to what's inside the bracket is going to change the input. And if you think about what the input is, it's x. So any change to the input is going to change left or right. Any change to the output, either out here or in front here, is going to be a change up or down because you're changing the output, you're changing what y is. So if we're changing what's inside the bracket, it's going to have a change left or right. If you're having a change outside the bracket, you're going to have a change up or down, changing the y coordinate. So if this is f of x add 2, it's going to go up 2. It's a change outside the bracket, which means it's changing the output. And what I would do is I'd just pick a few points and make them 2 higher, and then just connect those up. So I've just picked a few points there that were quite easy to do. Let's go that, and that. There we are. That would be the graph of f of x add 2. Now, what if you were asked to do f of x add 2 like this? Now, because that's inside the brackets, it does the opposite of what you would think. And it changes left and right. Now, annoyingly, you would think that f of x add 2 would go to right. It doesn't. It actually goes to left. So we would take this graph. This point would go here. This point would go over here. And this point would go here. So we'd end up with something like, oh, I can't draw it very well on here, sorry. There you are, something like that. So it's going 2 to the left. So outside the bracket, up and down, and it does what you think it would do. Inside the bracket, it's going to do the opposite of what you'd think. So f of x add 2, that we just drew there, actually moved it to left. And f of x minus 4 would actually move it 4 to the right, for example. Same thing happens with minus. This is going to be a reflection. If I do minus f of x, we said before that any change outside is changing the output, and therefore it's affecting it in the y direction, so the up and down direction. So it's going to change it in this direction. Now we know that minus f of x is a reflection, so this is going to go like this. And again, you have to forgive me for drawing it quite terribly. Like that. That would be minus f of x. That minus is not attached. Oh dear. Minus f of x. Like that. But then f of minus x, if we were to draw that one, oh, let's change the colour actually. If we were to do f of minus x, we're changing the input. And that's going to change in the x direction, left and right. So instead of being reflected in the x-axis and having a change up and down, we're going to be reflecting in the y-axis. So we would go, and again, forgive me for my terrible drawing, like this, up here, and then go down. So you can see that it's been reflected in this axis, and the change is left and right rather than up and down. So inside the bracket affects the left and right direction. It's affecting the input. Outside the bracket affects the output, so it's going to be the up and down direction. Again, you've got all the Haggerty numbers for that as well. Okay, I had to go slightly rogue with this, the recurrence relations. Essentially, this isn't too difficult if we understand the notation. So this is saying to get to the next x. So xn add 1 is the next x value. We need to do minus 2 minus 4 over the current x squared. So little numbers that are up top, it's still an indice. Down below this subscript, that's telling you what your current one is and what the next one is. So if we want to get to xn add 1, which is the next value of x, we need to do this sum on the right with the current value of x. So they're saying x naught is minus 2.5. So x naught is minus 2.5. Now to get to x1, they are saying do the sum with this one being x naught, and that will get you to x1. So if we do this with x naught, we'll get x1. So I'm going to do minus 2 minus 4 over minus 2.5 squared. If I type that in my calculator, minus 2 minus 4 over minus 2.5 squared. And remember, if you're squaring a negative in your calculator, you're going to need to put brackets around that. Otherwise, it'll go wrong. And that is minus 2.64. Great. Now, if I want x2, I'm going to do exactly the same thing again. I'm going to do all of this again, but I'm going to put x1 in this position. So to get to the next one, I'm always using the one before. So I'm going to go back in my calculator. I'm just going to use the left arrow, and I'm actually just going to put answer in that bracket. And that gives me minus 2.573921. And then to get to x3, I've got to do the same again. So I'm going to go back and put it in. Actually, I'll just click equals again. Minus 2.60376. Okay, and so on. So that's the values of x1, 2, and 3. So that one's really more about understanding the notation. If you want xn add 1, that's saying the next value of x, and xn is the value of x you currently have. So if this one was x1, then this one was x2, and so on. So it's just saying to get the second x, you need to use the first x. To get the third x, you need to use the second x, and so on. That's the recurrence relation one. Okay, by completing the square, find the coordinates of a turning point of the curve with equation x squared add 10x add 18. So y equals x squared add 10x add 18. Now, if you want to find the turning point, we're going to complete the square. To complete the square, you half the coefficient of x. So we're going to write x add 5 all squared. Now, when we do that, that's great, because x add 5 squared gets us x squared add 10x add 25. If you do 5x and 5x, yeah? So that's great. That's actually pretty close to what we want. So by halving this number, we've got pretty close. But we don't want 25, we want 18. So we always subtract 5 squared, because we want this term, but we don't want this term. So we're going to take away 25, and then instead we want plus 18. Doing that gives us x add 5 all squared minus 7. And that's y equals. That's it. We've completed the square. And once we've done that, and we want the coordinates of the turning point, so bear in mind this is a quadratic, it's a positive quadratic, so it's going to look like this. If you want this coordinate, then all we do is we look at our completed square format and we say, well, what value of x would make this bracket equal 0? And that would be minus 5. That is your x coordinate. And what value have we got at the end? And that's minus 7. So this one is like the opposite, but this one is just as it is. So I now know that this coordinate here is minus 5, minus 7. That is the turning point of the quadratic. And it's a quadratic because it's x squared. And I think that's it. It's a shorter paper for hire tomorrow. Yeah. So good luck. If you need any help, remember you've also got those Hegarty numbers. They are both on the Google Classrooms and here as well if you need them. 651, 435, 312, and so on. But they should be on your Google Classrooms if you need them. Thank you very much. I hope that's been helpful. Oh, wrong button. Bye.